Okay, well, we could sum all of this up and get the area of a circle, okay? Rather, though, than that, I'm going to put a mass density function in here, okay? Now, if we have a mass density function, rho of r theta, then the mass of the ij region, any typical region, is going to be equal to the density times the area. Now, if the density function is rho of r theta, okay, so I write this out, density function rho of r theta, then to get the density of the ij point, we evaluate that at some point within the region. We don't want to evaluate it at a bunch of points, since we're going to be taking limits. All the points in a given region are going to become closer and closer together, so there's going to be very little difference in density if we have a continuous density function between 2 points. And if we don't have a continuous density function, we can't do a single integral to evaluate it. Okay, so anyhow, we evaluate the density function at the point rij theta I star. Put the i's in my r's. Okay, and we multiply that by the area, which is approximate width times approximate length. I mean, you can call either of these length or width. These are the dimensions. This is one dimension, this is another dimension of our approximate rectangle. So multiplying the density by the area, we get the mass. So the mass of the ith slice being this whole theta slice, is what? Well, the approximate mass is, we sum from j equals 1 to m, because of course our ith slice has been partitioned on r from 0 to whatever, to a in this case, because we are looking at a circle. So we just sum all these up from j equals 1 to m. Now that should actually be an m sub I. So let's make those m sub I so I don't have to comment on that anymore. And while I'm at it, let's put the i's on the r's. Okay. Yep, I guess we need no, we don't. That was a mistake, because we've already gone to part of the limit. Okay, sorry. Okay, so the mass of the ith slice, then we get by summing up all the masses within that slice, and then we sum that up over all the slices. Well, we don't sum it up to, okay, I'm sorry. We're just doing the mass of the ith slice right now, and then we're going to total all the slices. Okay, not even looking what I've done, it's been a couple of days. The mass of the ith slice is this, and then we simply rearrange the order of these 3 factors to get the r's together, the r star together with the delta r ij, and ij here, and the delta theta sub I out here, because the delta theta I for the ith slice is constant. Okay, so we just factor it out of the sum, and we get this. And then this approaches an integral. Okay, this thing in parentheses here approaches the integral from 0 to a of rho of r theta I star times r dr. Okay, the integral of this quantity with respect to the r dr increment. Okay, and then of course that's times delta theta sub I. That's the ith slice. If we total it for all the slices, of course, we sum from I equals 1, and I thought that was an m, but it's an n, because I see from context, from I equals 1 to n, because theta was partitioned from I equals 1 to n. well, yeah, there are n partitions, okay? The partitions run from I equals 1 to n. The partition points run from 0 to n, but you need 2 points for every one, and so forth. Okay, okay, so the total is then going to be the sum of this integral over all delta theta sub I. So for every delta theta sub I, you have an integral like so. R goes from 0 to a in this case, because we are looking at a circle. And then this approaches the integral from 0 to 2 pi, because, of course, theta has been partitioned from 0 to 2 pi. So again, your R integral goes from 0 to a because R is partitioned from 0 to a. Your theta integral goes from 0 to 2 pi because theta has been partitioned from 0 to 2 pi. So we end up with this integral. Now, can't completely read the word increment, but I want to talk about the area increment. And that's this. And we never want to leave that R off because, of course, this R tells us that the further we get out, the wider the increment is, okay? So for a given delta R, an increment here is going to have less area than an increment out here. That's why you have to include the R in the R d theta. That's, of course, goes back to why we included it when we were developing the expression for the typical increment.